to speak to you to exchange some thoughts about epistemic planning. Okay, so you have heard Rajiv talking in the first session. Actually, he covered quite a lot of things I would like to touch. So we did talk about the sort of the planning of our two talks yesterday. But as you will see in the later part of the talk, multi-agent planning is much harder than single-agent planning. So although we did talk a bit, but I think I have to apologize that there will be some overlapping stuff. I hope you can. That's good? Okay. But maybe I will be doing some overlapping thing from probably a more philosophical point of view. I hope you will see probably some new things. Yeah. Okay. So the plan of the talk, I guess after Rajiv's talk, you already know the answer of this question. Now I want to be a little bit more philosophical to see the reflection of this. I mean, why knowledge matters in this planning setting, right? And I present a harmonic, mixed-blooded single-agent framework for planning. It's sort of the combination of DEL thing with something else. But I promise you it's relatively simple because I guess people are a bit tired before lunch. I hope you can follow me in the technical development. And in the end, I have a rather critical look of the multi-agent setting. Let's see what are the interesting questions for us to go further. Okay, so let me start with a picture. Actually, I'm not sure whether you know this fact that Chinese are famous for making stupid English translations of their Chinese signs in China. If you have ever been to China, you will see some funny English signs which are translated from Google Translation and this and that. So there are online groups collecting all these pictures, and now this is one of them. Actually, this is a real picture of a map near a, you know Great Wall, right? Near one part of the Great Wall. Yeah, so this is, you cannot see. Here are the places like temples and toilets and some parking place. And you are supposed to give them English translations, right? It seems there are some English translations, but if you look carefully, then all these things you are here. Yeah, I don't know why, but maybe they copied it from somewhere else or they made a mistake. So that shows, okay, so even I have the map, but if I don't know where I am, it may cause trouble for me to go to the place I want to go, right? This is sort of one instance of this whole general planning idea. So I want to go somewhere, but I have some uncertainty, right? So it will also become very bad if you are facing this situation. This is a map of Amsterdam. One of the famous things of Amsterdam is they have all these canals with the uniform name, blah blah gracht. So this whole long street is called something gracht, which means something canal. So even you know you are in this street, you have no idea where you are. And how do you go to, how can you make a plan to go to some place you want? So the usual thing you do is you walk around, you see more things, and you check with your map. Oh, on this map there should be a church, but I don't see the church, so I cannot be that spot in the map, right? That's the usual thing you do. So this kind of a scenario shows that when doing planning, one important thing is we are facing, we're facing some uncertainty. So let me put it into a very concrete scenario. So I guess some of you may have seen some episode of this Mission Impossible movie series. Okay, in this kind of movie, there is usually an agent in the sense it's really an agent. Yeah, so
the Chinese, what we get? When you translate the Chinese title, what?
It's a spy inside a spy, or spy of spy. Yeah, that's the Chinese. Okay, that's a good translation. Yeah. Okay, so this is a concrete scenario. A spy is sneaking in an enemy building, try to steal something, but he's a rather junior spy. And now some enemy spotted this guy, and they pull off the alarm. And this guy is in panic. He ran away, but for some reason he lost in this building. Okay, so the idea of this graph is a kind of a map of the floor he's involved. Okay, because he's in panic and he lost his way, he's not sure whether he's actually here or there. According to the map he has, there are some safe places for him to hide. But the trouble is, this is an enemy building. They don't put a notice saying safe in the actual place, right? You have to reason according to your map, right? That's the idea. Okay.
Another example. That in IMSC,
Yes.
very often I don't know whether I'm on the second floor.
Yeah. That's also. Yeah. That's yeah. The similar things. Okay, so we use this underlying thing to mark this is actually where the spy is, and the real spot. And we use this circle to mean he's not sure whether he's here or he's here. And we make very simple assumptions about the observability of this spy. Okay, so how can a spy know he's somewhere if he has the uncertainty and the map? He checks the thing he sees with the map, right? Yeah, for example, in this rather bad situation, he sees, okay, I can go on to the right or I can go up. But also it happens here, I can go right or go up. And for some reason, he excluded this guy because he thinks, oh, I didn't run that much, so it must be either this one or this one. But on these two locations, he has exactly the same observation. So you can do this or you can do that. So he has really no way to distinguish where he is. Okay. Yeah, let's go on. Okay, so this is the map with the uncertainty. And now we want to do some planning. We want to get this guy safe, to a safe place, right? And consider the following plans. Okay, first one is a very simple thing. You just move right. Okay, suppose this is sort of the order from the headquarters who is directing this agent. The headquarters may know the actual location of this agent, and they think, oh, you can just go right and you will be safe. But the trouble is, after doing this action right, will the agent know that he's safe? Maybe not. Unless the headquarters tells him, oh, now you're safe. Why? Because, okay, he's not sure whether he's here or he's here, and he moves right. What happens afterwards? He's not sure whether he's here or he's here. And notice that here they have exactly the same observations. You can either go right or go up here. You can either go right, go up here. So after doing this right action, he still has the uncertainty. He's not sure whether he's here or he's here. So he intuitively doesn't know he's safe. What about another plan? which is going up. So this is, again, a order from the headquarters. And the headquarters sees, oh, this is the actual word, so you can go up, then you will be safe. Then after doing this up action, will the agent know that he's safe? Probably yes. Why? Because he is not sure about whether he's here or he's here, but going up here, he will see that he cannot do anything else. But if he were here and going up, he can see, oh, there is an option for me to go left. So if he really does this action and come here, then he will know he's actually here, right? That's another plan. Okay, but maybe this plan is also not so satisfactory. Because why? Maybe the agent lost the communication with the headquarters. No one is guiding him. He has to find the plan to be safe by himself. So what he should do then? Okay, one way, very simple, is first go right, then go up, right? The thing is, no matter where he's here or here, after going right, then up, he will end up here, right? Either S8 or S9. But in any case, he will be safe, right? Okay, so in this case, actually before agent doing this plan, he already knows afterwards he will be safe. So this is a really subtle distinction from the second plan, right? Second plan is he did this action, and afterwards he knows that it's safe. But beforehand, he may not know that, right? So that's very subtle. Okay, this example is just to give you some ideas of the subtleness of this epistemic business. So let's come back to our question, why this knowledge matter, right? Okay, maybe, yeah. So for me, why knowledge matters in this scenario is because we have uncertainty. In the previous case, we have uncertainty of the initial state, but actually we may have other uncertainty about other things. Yeah. So to handle this uncertainty, we need to use the notion of knowledge or belief. And the planning with epistemic goal is to turn this uncertainty into certainty of the goal. So that's my understanding of this epistemic planning, the general idea. Okay. So what are the sources of uncertainty? Yes, please. Yeah. I think uncertainty is just a general word. I mean, certainty is a general word. So, yeah, I think it's debatable philosophically, but maybe here you can just equate them. Yeah, so, yeah, I don't know actually. Yeah, but if you are talking about uncertainty, usually many people would think probability, right? Yeah, and probabilistic kind of belief. Yeah, so anyway. So the sources of uncertainty. I said, okay, maybe I'm not sure about the initial state, or some actions have non-deterministic result. Like I want to open the door, but the door is locked, and I just couldn't open it. I mean, beforehand, I don't know what will happen. And yeah, maybe we also have partial observability. Like in this example, the guy can only observe the available corridors or available actions. But maybe he can do some kind of sensing action. He can knock the wall, or he can ask people, right? He can have more information about where he is. Okay. This is especially important in the higher order multi-agent case. I mean, if you want to reason about higher order knowledge or belief about agents in a multi-agent case, then what you observe is not only about the facts, but also about how the others are observing you and observing others, right? Okay. And because we have this kind of uncertainty, we have different planning models, or say different planning problems. For example, here, this column is for whether you have uncertainty for the initial state. Here is what is your observability. Either you observe everything where you are, or you observe nothing, or you observe partially something, right? And this is whether you have a non-deterministic action, and in the end, whether you put probability into it. So this is a relatively rough picture of different planning models used in AI planning. So you have classical planning, no initial uncertainty, full observation about the state where you are, and you don't have non-deterministic actions, you don't have probability. And this is called a full observational non-deterministic planning. So you don't have initial uncertainty, you have full power of observability, and action may have non-deterministic effects, and you don't have probability here. And this is a Markov decision processes, and you have probability, and you don't have initial uncertainty and this. So you can see you have all these different planning models, right? That's the big picture. Because you have different sources of uncertainty. And to handle these things, you need probably different techniques. Yeah. So in the later part, I will be focusing on this conformant planning. So maybe this is good to just say something about it. Conformant planning, you have some initial uncertainty, but you don't really have observability. And for actions, you have non-deterministic things. The tricky thing is you need to make a plan without getting any feedback during the execution. Yeah, it's like you cannot just say, oh, I make a plan for traveling to IMC if I'm at the CMI or I am at the IIT. You need to make a uniform plan, which can work for anything. Maybe the uniform plan is just to call the taxi. That's easy. Okay. So also depends on whether you can get the feedbacks during the execution of your plan. You also have different forms of plans, right? In the simplest case, if you don't have any observational power, then the plan is naturally a sequence of actions. But if you can get some feedback when you are executing the plan, probably you can use a conditional plan, or sometimes a program, or say a policy on which state you should do what, something like that, right? This is interesting to see here. Actually, although this sequence of actions is very simple, but it's very useful, because even sometimes you can have some feedback during the execution, but you may not be able to afford the cost of the feedback. Maybe you are short in time, you need to pay a lot to consult experts. So even in the cases you can have feedback, sometimes you prefer a very simple, straightforward sequence of action to just do it. Yeah. Okay. So planning is just to try to reach some of the goal states, like in Rajiv's talk, but under uncertainty in this case for epistemic planning. Okay, actually in planning, people often care more about to minimize your expected cost. For example, you may have different plans, right? To all reach, say, similar goals, but you want to optimize your plan with minimum goal, yeah. I mean, minimum cost, right? But in this talk, I won't talk about this cost thing, so that's a warning, okay? So how does knowledge come in? So there are several places where you need knowledge. First of all, the goals can be encoded by epistemic formulas, or at least something about knowledge. But it's interesting to mention that in usual AI planning, they only care about to make sure you know something in the end. But in the more controversial planning, especially with multi-agent, it's also important to know to let the plan to guarantee someone doesn't know something, or even you are the headquarters, you are guiding this agent to go somewhere, but you don't want to let this agent to know too much, right? You want this agent to know that he's safe, but you don't want to let him to know something secret. Right? So negative things are also interesting, but it's usually not handled in the AI planning, because usually there the goal is a set of states. You just want to reach one of them. But you can think about what if the goal is negative knowledge formula. So what kind of corresponding goal set is that? Yeah. Okay. So also knowledge comes in when you need to make a branching structure in your plan. So if I know this, I do this. If I know that, I do that. Why do you need to use knowledge? Because, okay, so if you want to really execute this plan, it must be dependent on your knowledge, not just the fact, right? It depends on your knowledge. Also, in the end, you want to make sure the planner also knows that the plan will work. Yeah, you don't try out just a random thing. You need to make sure the plan is working. Yeah, like in this previous example, the second plan, although in the end the agent will know that he's safe, but before doing this plan, he doesn't know, right? Yeah, okay, here are some places where knowledge may come in. Yeah. So roughly speaking, classical planning is kind of a reachability in this state space of evaluation of facts, right, to reach certain goal. And epistemic planning is reachability in a much larger exponential, maybe, knowledge space. So each point, each state is a sort of a knowledge state. The description of the facts, the state of facts, and also the description of the knowledge of the agent. So you can think it's reasonable to maybe translate some part of the epistemic planning thing to the classical planning by actually, we got a remark from the audience, right? This is just one example. There are really a lot of work. I didn't have time to put out this thing. So you can maybe check this and you will see that.
Can we say that would be maximal? I mean the transformation.
Yeah.
So this is maximal transformation we can do.
What do you call it maximal?
I mean maximal in the sense some part of this representation you will be transferring to the classical planning, right?
Yeah.
So can we reach to a maximal that up to this much we can transfer?
Yeah.
Is it a hard problem?
I think there are some sound and complete translations, right? To really transform some, for example, conformant planning to classical planning by.
Okay, so one more question. So what extra thing we do in contingent planning which makes it partially observable from conformant planning?
Contingent planning.
Contingent planning is partially observable. Conformant is not. So can you differentiate quickly, because I'm not able to recall.
Oh, it's just the conformant planning is you assume you don't get any feedback. So for the plan to work, you have to make sure in any of the possible initial state, the plan will be able to execute it, and in the end, it will work. Contingent planning is, in doing it, you may get feedback. So your plan may be a branching one. That's the difference. Yeah, but no probability. Yeah, that's more or less the, okay. Yeah, I should spend more time on this table. Yeah. Okay, so there are translations. Yeah, but you can imagine there will be at least exponential blow up. But people have come up with very smart ideas to code things. So you don't need to always have the exponential blow up in practice. Sometimes you can do better. Yeah. Okay, so also because I will present this mixed blood thing, it's a logical approach. Then a natural question is, okay, in AI planning we have all these algorithms, very nice. Why do you want to do a logical approach? Okay. So first of all, maybe as a kind of a background. So in this summer school, winter school, or what do you call it? In this instructional seminar thing, people often talk about modal logic, but I doubt whether all the people get the idea of modal logic. What is modal? It sounds weird, right? To people who are not into philosophy, maybe, or linguistics. Okay, I just give you some background, and you'll see why we use epistemic logic later on. Okay, so to put it in a very rough and rough concept, modality. So first of all, modal logic is logic about reasoning about modalities. And what are modalities? So the basic, very simple idea is there are modes of truth. What do you mean by modes of truth? I have truth, right? That P is true. What is mode of truth, right? So mode of truth is this P is true in what sense? Yeah. So usually we say P is true. That's in the true-false sense. But sometimes we say different things. For example, we may say it is known that P is true, right? So it's not only P is true, but it's also known. And for example, in Olivier's deontic logic, P is permitted. So P is not in the true-false sense true, but it's permitted, right? So or in temporal logic, P is eventually true. So it's not true now, but it will eventually be true, right? So that's kind of a different modes of truth, if you like. And the important thing is to separate the plain truth from those sort of mode-dependent truth, right? When you say something, you can say, oh, P. Maybe sometimes when you say P, you also say you know that P. But what about you don't know that P? So what can you say not P? Or yeah, you need to have some linguistic stuff in it. And these stuffs are these kind of modalities, right? Okay, so
does there exist any theory of truth which covers these kind of things also?
Oh, I think there are theory of truth in terms of modal logic. Yeah, I have seen the thing. Yeah. Okay, so yeah, speaking about these translations, if you remember, from the epistemic planning to the classical planning, one idea is to add a lot of artificial propositions which are used to express knowledge or ignorance. That's the idea. So you really need something. Even you don't call it a kind of modal logic, you need something to differentiate P from you know that P, right? Okay, so why do we use this epistemic logic? First of all, it's very natural to express some properties. You want to make sure someone knows something in the end or doesn't know something, or someone need to do some action depending on whether he knows it is 2 o'clock or 4 o'clock. So, right, it's natural to express things. And more importantly, it's philosophically grounded. Because this modal logic came from philosophy, and we have a really long history of discussing the meaning of those modalities. It sounds a little bit too much philosophically grounded, so let me change another word. So they sound right. I mean, maybe that's a more, how to say, modest claim. So they, after you think about a lot of time, then you may come up with something sound right. And if you have this kind of thing, this may probably will let you to go further. So in AI or say other field of computer science, you have many things which can work. But the thing is, they may not work in the future. They may not work in other situations. And to have some philosophically grounded approach, maybe you can go further in the future. We'll come back to this later on. But this is one of my points. Okay, and also we have a lot of existing meta theorems about this kind of logic and some also computational tools to use them. Of course, you need to do something, some more things, but at least this is a well-established theoretical field. Yeah. And also, maybe this is just a hope. Maybe we can handle a richer class of problems by having a language to describe them, a logical language to describe them. We hope we don't have more costs, but this may not be true. I will come back to that. Okay. But I guess some of you may not be satisfied. I mean, this is, yeah, so what, right? We'll come back to it in the end. You will see after maybe you see my framework, maybe you will probably understand better there can be other advantages. Okay, that's it. Some warnings. So in the next part, I will present this mixed blood thing, bloody mixed blood thing. So some warnings. I won't talk about, for example, probability or optimality on cost, no heuristics, even probably no detailed algorithm. And it's single agent, it's simple stuff. And more importantly, this is a rather departure point from Rajiv's talk. So we will be using explicit transition models. So usually in AI, they use, of course, you have seen already this description language to make a very compact representation of the problem. But to be more philosophical, you need to go down into the sort of core of the problem, and we sort of abstract away this compact representation thing. So we go directly to the transition system. So the planning is based on some transition system with states, and you want to go from some states to other states. That's the core thing, right? Okay, this is the warning. Okay, so we hope, although this framework is relatively simple, it's lightweight, if you like, it's lightweight dynamic epistemic logic with something else. But we hope, although we don't talk about these things, but we can see the most important logical aspects in this whole planning problem. That's my hope, yeah. Okay, let's go into the next part. So what is the most important thing for artificial intelligence? Probably at least two things. The machine should, to some extent, think, processing information, do reasoning, and to move, right? To think is to move, so to speak, because we have to survive in a way. So think and move correspond to probably two notions, like knowledge and action. Of course, think is reasoning about the knowledge, and move is not just action, but the planning, but for strategy, all this, okay? So there are two major modological approaches to handle knowledge and action. Yeah, I think previously Hans maybe has already mentioned. One of them is epistemic temporal logic. So the idea is, okay, you have a temporal, it's from computer science. You have temporal logic to reasoning about the behavior of systems, right? In the future, something should be available to you, and in the end, yeah, you want to make sure some process never die or something like that. Okay, but to use it in a distributed environment, you need to talk about the information which are not shared by all these processors. And a natural notion comes also from philosophy, is just this knowledge, right? So it's very natural to add the epistemic stuffs on top of temporal logic. So it's temporal logic plus epistemic stuff. So it was developed initially by Halpern and his friends, and also Rohit Palik and Ramandu Jam. Yeah. Okay. Another thing we have seen a lot is dynamic epistemic logic. So in some sense, it should be called dynamified epistemic logic. So the basic thing is epistemic logic to reason about knowledge, and you add sort of action to it, and to let knowledge evolve, right? If you just talk about static knowledge, it's kind of boring, right? Okay, and we have heard really a lot already about it. Okay, so two things.
So the first epistemic logic is applied over temporal logic or the other way?
Oh, it's first temporal logic, then apply epistemic stuff. So that's why I call the ETL, not TEL, right? Yeah, and this is DEL, not the EDL.
Yes, which was considered at some.
Yeah. Actually, okay, this is double meaning. It's also dynamic in the dynamic logic, because at the beginning of DEL, they really try to put the programs into this dynamic epistemic logic. But for now, I think it's more reasonable to call it a dynamified epistemic logic. To me, I mean, that's my own opinion.
Except that maybe it's not a verb, right? Is it a verb?
Dynamified.
To dynamify?
I don't know.
I know what you mean.
I don't know. I guess not. I guess not. Yeah, we will see a lot of strange things. For example, there's a conformant planning. Conformant is not a word. It's kind of creation of, yeah. Really? I checked the dictionary, it doesn't show. Yeah, okay. Anyway, yeah. Okay, two approaches. Our framework is sort of based on the ideas behind these two things, not on the exact framework. Yeah. Okay, from a sort of a model theoretical point of view, a logic framework is a triple of three things: a logical language, some class of models, and you have some semantics to give what kind of sentences are right on what kind of models. Okay, so for ETL, in the language, you have two kinds of modalities. One is about time, say eventually something will be true, and something about knowledge, this K operator. And in the model, you have both temporal and epistemic structure. I will show an example later on, so don't worry. So you can view this kind of logic as two-dimensional modal logic. So you have some structure like this, and you have other structure like this, and they have sort of interaction, right? And the semantics is very simple. It's, well, except that you probably need some fixed point operators to handle the temporal part. But if you stick to the very simple modalities, then they are just creepy key-like. Well, yeah.
So I didn't understand the difference between like putting temporal structure over epistemic and epistemic over, like.
Yeah, I will. Yeah, you will see the example. So the semantics is like a box phi is true somewhere in the model, if and only if for all the accessible word, this phi is true, right? That's the basic thing. And the dynamic epistemic thing, in the language, you have knowledge and you have some events or actions. And in the model, it's purely epistemic model. So this is a really big contrast to these temporal epistemic stuff. And in the semantics, for the knowledge part, it's creepy key, like simple thing. For the event part, it's kind of a dynamic semantics. Yeah. The idea is the meaning of action is the potential change it brings to the knowledge state. So meaning as changes. That's the basic philosophical idea. Okay, example. So this is sort of a very simple temporal epistemic model. You have the epistemic stuff, the indistinguishability links, right? But you also have a kind of temporal development of the system, right? You go from here to here. And on this world, you don't know whether, you don't know that P, right? You consider this both possible. But after, in the future, at some point, you will know it. Because here you don't have the another option anymore, right? That's the basic idea. What about the dynamic thing? So first, you should cover this. This is the epistemic model for dynamic epistemic logic, and you don't know whether P. And then someone says P, and you trust this guy, and then you delete this part, right? And you end up with one singleton model, and where you know this P, right? So you see the different. Did I answer your question? No. Oh, I didn't get your question then. Yeah. Yeah. I don't know exactly what is TEL. There is no this thing maybe. Yeah, but to have this name is just to mention to record the history of the thing, right? Because here these two things are sort of diagonal. Yeah, it's no matter whether you first have this or first have that. It's kind of diagonal. Yeah, so I don't know. It's more like when you when you write down your name, you have your father's name somewhere, but it doesn't matter. It's just to record your history. Yeah. Okay. So, but for this thing, if you keep track of the model changing from this model to this model, and you build some kind of announcement links or other action links, then you will see, oh, this picture looks pretty much like this picture, right? It looks so similar. Yeah. And that's the basic idea underlying many of our techniques. So we see similarities between these two things, right? Okay. Oh, this is just to remember. If someone asks you, oh, you have listened to all these DEL talks, what is DEL? At least you can say one core idea is that action are changes to epistemic states. Yeah, you can go back to the MIT philosopher Robert Stalnaker, I think in 1978, on assertions. Yeah.
So why do you not want to put an announcement of not P on the right-hand side there? Then they would be really simple.
Oh yeah, yeah. I should. I should have done that, but yeah. No, I don't. Yeah. Okay. So let's go back to this picture. So we have seen the difference and the similarities between the two. And what we want to do now is the third, the mixed picture. So in the language, I want to have both knowledge and some action or events. In the model, I want to have temporal structure and some kind of epistemic stuffs. But the tricky thing is, I want to interpret this temporal structure in a more dynamic way. You will see what I mean by that. But the reason is you see, okay, this planning thing to the core, technical core is some kind of reachability in space, right? And it's intuitive to have the space as the model. I mean, if you care only about the technical core. So that's why we want to have the temporal structure. And it will help us a lot to make the framework simpler and more to show the instance of the planning job. Okay. But usually such logic cannot be reduced to, say, either the temporal part or the epistemic part. because you have two kinds of structure. How do you eliminate one kind of structure in the model? It's impossible, right? So that's the intuitive idea. You cannot do the usual DEL trick of reductions, but it's not a problem. In the recent work, we developed some general techniques to axiomatize DEL-like logics without using the reduction axioms. So it's no problem. So it's not, for me, it's just reduction is a very nice coincidence. Yeah, I like it, but we should also go beyond that. Yeah. Okay, so that's the basic idea. Let's be a little bit more formal. So actually, you don't need to read these definitions. The idea is very simple. So the model for our logical framework is just things like this. Basically, it's a Kripke model with label transitions and some declaration about truth, facts, and a circle. This circle just to denote your uncertainty set. Very simple. Just a graph with a circle, so to speak. Right? So it is shown here. This is a Kripke model, and you have a circle, set of these states. The only thing you need to make sure is it's non-empty. You don't go crazy. I mean, you think you are somewhere. You are not, well, but maybe when you are in your student age, you think you are nowhere. So, yeah. But anyway, so one condition. So in this uncertainty set, all the states should have the same available actions. So, I forgot to put the definition of ES here. So ES is a set of actions you can do on this state. So this is corresponding to our story, right? At least you should know what are the available actions. Yeah, please.
It's defined by the RA relation.
Sorry, RA is just this kind of thing.
Right.
Oh yeah. Yeah. Yes. This thing is from RA. So the outgoing labeled A transitions. You just check that. So you don't count. You just say, oh, here I can do AB, here I can do ABC, right? Then they are not different. They are different. Yeah. Okay. Remember this picture? Just a circle with a graph. Very easy. Yeah. Okay. The language is also very easy. Knowledge action. So here is a diamond form of action. So it means after doing A, it's possible that phi is true. So it's remember this modality thing. It's not phi is not true here, but after doing A, it's possible true, right? That's the mode of truth. Okay, so we use this funny k hat. Also, Hans used that to denote the dual of k operator, right? That's very simple. Okay. Yeah.
So
yes.
the uncertainty set is like going to a multi-pointed model.
No, it's not. Yeah, you will see. Yeah. Okay. So yeah, actually, I should have explained. So this important thing. So MS is a pointed model if S is in this uncertainty set, right? Yeah.
Can I think of this as an information partition?
No, because it's just a circle. You don't have partition. Yeah. Well, you can think. Yeah. It's an easy partition. Yeah. Yes. Yes. Maybe you can think about that. But if you do it in the multi-agent case, then it's kind of different. Yeah. Okay. So the truth condition is very easy. So for this, remember if I write something like this, then it means this is a pointed model, and which means S is in this circle of M, right? And okay, so then you can interpret K phi. So K phi is true on S if and only if for all the states in this circle, phi is true, right? Very simple. Another thing is a little bit more complicated. So remember, we say action as changes. So we need to change something. So yeah, please.
You have just only one subset taken?
Yeah, just one. It's a single agent thing, just one. That's the fundamental difference between our work and all this two-dimensional logic. Yeah. Okay, so this diamond A phi is true if and only if there exists T, S can go to T via A, and in some new model, this phi is true. What is the new model? It's almost the same, but you update your circle. How do you update your circle? It's very easy. Intuitively, you sort of carry your circle while you move forward, and you check with your observation. Very simple. So 2 steps. First, you carry your circle forward, and then you check with the observation. Actually, this is just a special case of the general observation thing. I want to make it concrete, so here ET is, okay, I don't need to explain this. Let's see the example. You will see how it works. Okay, here is the model. So this is the pointed word. This is a real word, right? And here is a circle. And you do B. What do you do? Well, how do you update the model? You take the circle with you, right? In what sense? If this thing is in the circle, then you do B, then this thing is in the circle, right? And you take it there. And then you check with the observational power. So here you cannot do anything, right? Here you also cannot do anything, so it's fine, right? Let's see another, then you can verify that K not P is true initially, but after doing this B, you don't know whether, you don't know that P. Yeah, actually when you put the negation in front of K operator in natural language, you often mean you don't know whether P.
So,
yeah.
So if you don't put P, it means not P is true.
Sorry?
In the picture when there is no, where there is no P.
Oh, yeah, sorry. When I don't put P, then it's not P. Yeah, that's, yeah, sorry, I should have mentioned that. Okay. Remember this picture, yeah.
So what do you put in the new circle? All the states that are accessible by the same
Yeah. Yeah, and you do something about the observation, which comes in the next example. Okay, so let's do something else. The same starting model, and you do A. What will happen? You see, like in this idea, you take the A with you. So then from here you have A, so this should be in the circle. And from here, you go A, this should be in the circle, right? So first of all, these 2 things should be in the circle, but you need to check it with your observation power, right? If you really do A, then you will end up here, and you will see you can do B, right? But if you were here after doing A, you will see nothing, right? Because actually, after doing A, you will be here. You will eliminate this possibility according to your observation. Because here you observe a B thing, and you check it with your map, and then you find it out, well, I couldn't be here, so I just kick it out. So in the end, you have this singleton circle.
Right. So why don't you have 2 circles?
You don't produce more babies.
Expect 2 singleton circles, one over S2.
No, it's about the real world.
It's about the real world. Oh.
Yeah, because just recall this example of having a map, but you still get lost. Yeah. Okay. So you check with your actual observation, right? Yeah. So you end up with 1 circle, and then you again do 1A, and of course then you have this, right? But now there is a very funny thing. You see, you start from the same thing, right? And you end up with the same actual state, but your circles are different, right? So here, finally, if you go to this state, you don't know P, right? But here, you know that P, right? That's the funny feature about our semantics. It's path dependent, right? Yeah.
Yeah, you ended up with the same circle, but you also considered actions.
Sorry?
But you also considered actions.
Yeah.
That's why perhaps you ended up with the same node, but with different meanings.
Yeah, actions you just hypothetically you move forward. Yeah, that's also fine. Yeah. So Olivia, you.
So, what would be a real life example that illustrate that sort of cases?
Yeah, we go back to the Mission Impossible, right? Yeah, we will go back. Yeah. Okay, so this is just to show you some tricky things. Yeah, if you go to the same point from different paths, the formula of, the truth value of K formula may change. Yeah. Okay, so special features, yes.
Once you reach the goal, do you discard your actions?
You discuss.
Because you've reached your
Yeah.
state, then you don't need the actions.
Yeah.
You mean, do you
But
have
you don't delete actions in this framework. Maybe you can in the future. You just don't care then. Okay. Any?
one more question?
Yes.
So, what surprises me is that you implicitly have in this model that the agent in each state is indeed aware of the actions it can perform.
Yeah.
So, if you execute an action, you immediately observe the future action.
Yeah. This is what I assume. Yeah, it goes with the sort of this uniform strategy in game theory. So at least you should know what kind of things you can perform. Yeah. So this is actually just one example of the observational power. So you can replace it by some arbitrary observational token, and you can do it in the AI kind of style. That's also fine. Yeah. Yeah. Yes. Yeah. Yeah. It works in this, for example, this map setting, right? You should see, what kind of streets are there, or what kind of corridor. Yeah.
Yeah, but in the spy example, it's natural to think that when there's uncertainty about your location, there could also be uncertainty about the actions available.
Yeah, exactly. Yeah, but there is those. Remember this map thing? The transitions are not actions actually, but they are corridors. So I mentioned that section, but that was wrong in this example. They are just this map is just a map. There are then these corridors. Either you turn right or you go straight. These kind of things.
Sorry, I don't want to interrupt again, but I do interrupt again. But in fact, what you assume in this map example and in this planning example is in fact, a common knowledge of the whole model.
Yeah. You have the map. Yeah. Exactly. Remember this thing. So just take it as a map with you, and you don't know where you are. Yeah. But maybe I should speed up a little bit. Otherwise, I cannot. Yeah. Yeah. Okay. So some features about this semantics. So knowledge is sort of path dependent. It's not really path dependent. There are tricky things, but you can see it's funny features. And actually, if you think about these two-dimensional models, this U thing is just a snapshot of a unraveling of the temporal epistemic development. So if you like, And importantly, we say a formula phi is valid if for any legal pointed models, phi is true. Right? Remember, this S should be in this uncertainty set of M. Otherwise, you cannot interpret these K formulas, right? And it makes sense because you go, you always move, right? How can you be somewhere? But this is kind of assumption. You always consider possible that for the real location for knowledge. Yeah, this is a assumption. Okay, let's go back to this. I hope it can clear up some confusions. Okay, so if you go R, and then you will end up with these two things as the new circle. And you will see that actually, because you go R, then you end up with S4, and it's safe, but you don't know it's safe. Yeah, if you go up, you're safe, And you know you are safe because you first carry the circle and you check this guy with the actual observational power here. Then you kick off this guy, kick away. Yeah. And the final thing is you know that after doing R and U, you are safe, right? You take the circle with you and then up, then you will end up with here. And you know it because in any case, you will end up here. You can verify this. Yeah, okay. So some theoretical aspects. First of all, we can have a special normal form of all the formula in this language. We can push the K outside all the action. And because it's sort of S5 thing, so in the end, you just need one level K, and in the end, in the scope of K, you have a lot of action stuffs, right? And this thing will give some idea to come up with some bisimulation notion if you know what is that. If you don't, it doesn't matter. And you will have finite model property. Yeah, and you have a sound and complete axiomatizations here. You have rules. In particular, you have substitution rule, which is not usually there in the dynamic epistemic stuff. Yeah, and you have axioms. For axioms, I always hope axioms are clear enough in themselves. You can read from them what they're saying. For example, the usual K thing. And this says you can always observe what can be, what actions are available, right? And this thing is usually called perfect recall. So it reads, you know after doing something P holds, then after it, you know it. It's like you don't forget, right? Beforehand, you already know what you will know. Then after doing that, you don't forget. This looks a little bit complicated, but let's see the essential structure of the formula. So actually, this is in this structure. So if A is possible and you know that P, then you know that doing A will get to P. So it's sort of a no learning thing. So if you learn something, if you know something afterwards, then you know it beforehand. But the important thing here is this is a diamond. And if you compare these two, if you put a box here, then you have a by implication here. But actually, this is one of the secrets of DEL. So in DEL, you learn things, right? Some guy announced something, and you know that. You learn it, right? And the reason for you to learn is that this no learning kind of thing only works if this action is executable, right? In the public announcement case, why can you learn this P after someone announced P? Because you assume the announcement is truthful, and on the not P word, this announcement wouldn't be announced. So you kick out that thing. So actually, this is one of the secrets of DEL. And you don't need to take care of the complicated coding of the available actions. So it doesn't matter. You just remember this kind of structure. Actually, we can give a similar axiomatizations for public announcement logic. And there, you'll probably see some more things like besides literally this thing and this thing, well, you just need to replace A by some phi. And you have something like this. Sorry, I must have said here. Yeah, which says you don't change the truth value. And also you have this thing. So you can announce it only if it's true. And plus this thing and the usual modal logic stuff, you will have a completeness of public announcement logic. Okay, but here I want to emphasize in the past 2-3 days, you have seen a lot of axiomatizations. But why do we do axiomatizations? Why do we care axiomatizations? Of course, it's kind of a technical result, typical technical result for logicians, but I think we do it for some good reason. For me, it's like okay, you define a language, a semantics, but you want to know whether your semantics is sort of okay, intuitive. The way to know it is to see whether under this semantics you may have weird true formulas or valid formulas. The way to do it is you completely capture all the valid formulas by some syntactic proof system. And if in this system all the axioms are very intuitive and you like them, then it gives some idea whether your definition is okay or not. So for me, at least, this is the important part if I want to define a semantically driven logic framework. Yeah. Okay, so a short summary. So model is very compact, language simple, and the semantics is dynamic and epistemic plus some temporal kind of temporal thing. And we want to use this thing to track beliefs, knowledge, and do plan existence or plan verification. Let's go to the more interesting part for planning. Okay, we focus on the most simple epistemic planning thing, conformant planning. So idea is, again, okay, given some initial uncertainty, suppose there is no feedback, find a sequence of action which will always guarantee the goal. That's the idea. And it's like what I said, the conformant planning for go to IMC is just no matter where you are, call a taxi and tell them. So that is. Because you mentioned this CMI stuff, right? I mean, that's the context. Okay. So now we simplify the semantics a little bit because here no feedback is available. So we just don't, in the semantics, you see here, we just actually, you see here, we just don't check with the observational power. We just carry the circle around, right? That's the simplification to fit this very simple planning case. Actually, it's not that simple planning case, but we'll see. Yeah, so this is simplification. And okay, so let's formulate conformant planning in this logic. What is a conformant plan? So first of all, I need to define this shorthand for this conjunction of diamond and box. So in planning, it's important that you have to make sure it's actually executable, and by any execution of the action, you will have some phi, right? So it's important to have both. I'm not sure why we define the diamond and box without, why we define diamond without the executable part. Actually, I have some idea about it. It's a very interesting logic. Okay, so the conformant planning is to find the, here is a given set. It's a subset of action because I don't want to use all the action. I just want to use some of the actions. And your goal is to find a finite sequence of actions in this B such that this formula holds. It says actually after doing A1, A2, A3, AN, phi holds. But the thing is you have to make sure it's always executable. So if there is one case it's not executable, then it's not a good conformant plan. Yeah, for conformant plan, some people also call it a strong plan. It's really strong, no matter what happens. I mean, it works. Okay, so but to actually handle the existence formula, existence problem for this conformant planning, we need something more. But before that, let's see. Okay, go back to the example. So this RU is clearly a conformant plan. So you go R and U, you always end up with safe. And it's always executable, right? Okay, so you can check this formula. So in the end, you want to make sure K safe. You know that's safe. And actually, by checking all the U in this formula is just to check whether you know this whole thing, right? Yeah, the planner should know this thing. Yeah, okay. So about the existence of unbounded conformant plan, we need to use some more heavier machinery. So Sujata talked about this PDL like program constructions, and you have tests, you have sequential non-deterministic choice and iteration. For example, you can express that I know if I execute this program, well, I don't know P do A until I know it to do B, then afterwards I know this. So you can see they can do a lot of very complicated knowledge programs, right? And in the semantics, for A, it's just usual, the previous thing. And for this, you need to sort of do the composition of the program. Yeah, but I don't have time to go into this. But it's just like the PDL stuff, if you know PDL. Okay, and recall that conformant plan requires this kind of thing. So how do we make sure, how do we express there exists a conformant plan? The formula is this. So intuitively, it says you can only use these epistemically conditional actions. Like you have to know this guy is executable, and then you do A, right? You have to make sure it's always executable, and you don't know how many times you will just repeat. And there is a non-deterministic choice between all these kind of actions, and then you do the iteration. And afterwards, you want to make sure K phi. That's the formula which corresponds to there exists a plan such that this thing holds for all the U in the big U. Yeah, that's the formula. For example, if B is just A1, A2, and then this formula is just whether you can do A, you test, and you do A, or you do A1, or you do A2, and I don't know do how many times, and then afterwards I know phi. Okay. Okay, so I don't want to go into this, but it's well, maybe it's not that intuitive at the first glance, because this thing should be simple, right? I mean, you just say, oh, there is a plan. Why do you need all this condition? And why do you put K to the end, not at the front, right? You may ask. So for example, why doesn't this work? So this sigma B means all the plus of all these things in the sigma, and you do the star, and you use this special modality, right? Why this cannot work? Because of the kind of a didicto deray rating in the philosophical term. The central idea is if you say, I know there exists a plan that phi holds, this may mean two things. One thing is, for example, this thing, on each of the possible state, there is a plan to make sure it. Or there is a uniform plan to make sure it, right? This is a little bit subtle for people who are not familiar with the first order modal logic. Anyway, so two readings of this. You know there exists a plan can mean that for each thing, you know there exists a plan. But this plan can be different. Or the plan should be the same. We want the second reading. So this guy doesn't work because in this example, there is no conformant plan, but on each state, you have a plan to make sure P. So it's bad. What about you leave out the K in the end? So it was K phi, but now I just say phi. What about this? This also doesn't work. And okay, so I think I need to rush a little bit. So anyway, there are tricky things. It's not that straightforward. But after doing all this, you will understand better about the conformant planning. Okay, so how do we do model checking of this thing? Because we say we can transfer the plan existence problem to a model checking a formula in our language. How do we do that? The trouble is the usual global model checking algorithm for modal logic doesn't work because this thing is path dependent. If you know the global model checking thing for modal logic, you should think, oh, first you compute the subformula, whether subformula is true on which kind of state. But now you cannot do that because whether subformula true or false on some state, it depends on where you go, how you go to this state. So the usual thing cannot work. So we can have alternative semantics, but we can keep the model. But we keep the model the same, but we use some context to record the change we need to make in the semantics. So this will give you a sort of recursive local model checking algorithm if you don't do stars. With stars, it's still more complicated. We are still working on that. So there are some complications, but I think we can handle it. We have proved also a p-space lower bound, and we guess maybe maybe it will end up with exponential time. I forgot to put Wei is Yanjing Li, with whom I did the Pure's basic framework, and Chuan Yu, a student of Yongmei Liu. Yeah. Okay, so I really need to speed up. After showing you some of the techniques in this framework, I want to go back to this logical approach thing. What are the advantages? So you can see we can express complicated goals, and we see subtleties underlying all these planning things. Actually, this is conformant planning is the simplest one, but it's already, you see a lot of knowledge assumptions. It looks easy, but if you look into that, it's more subtle than you think. And especially we can use specification language to talk about the plans. I don't like to just mention the plan as some abstract object intuitively. We need some language to talk about it. And then we can compare whether two plans are equivalent, whether one is kind of a refinement of the other by cutting down some part of it. Okay, in principle, probability can be plugged in, so you can base your model on this MDP-like stuffs, right? And in the end, we want to show, to extend our framework to a sort of base framework to compare all these different planning problems. So in the future, that's the basic idea. Okay. Yeah, but the thing to extend it to multi-agent setting, we need some more ideas. One of them is another core idea of DEL, which is this action model. So I don't have time to talk about it, but let's go to the last part of a multi-agent case. Okay, so actually without epistemics, it's already interesting, like Rajiv showed two robots handle the same table. In some other cases, although the agents are the same, you need, for example, some thieves want to steal a diamond. Someone should press the button outside the room, and this guy takes this and press again, and they go. So something like that. But also for agents with different abilities, it's more important. Maybe someone have more ability to do something, and you need to plan. Okay, it's really important to have a better understanding of the necessary cooperations. Like, okay, how many agents do you need to do this job even without epistemics? I have seen some work, but it's very limited. So I think there are quite a lot of things to be done even without that knowledge. For multi-agent thing, so the goal formula may involve some higher order knowledge, which requires some observability thing. And to understand, actually, Rajiv already talked about it. So now to use this DEL-like approach, the important thing is I have action models to capture higher order observational power, and the states are pointed epistemic models. Actions are just action models, probably with factual changes, and state transition function are just this update product stuff, right? Yeah, and for example, how to let agent I know secret number and others merely know that I knows, but they don't know the number. So I can simply write down a number and I give it to Hans, and you all saw Hans receive the number, and he, yeah, probably I should actually write down the number. Yeah, okay, anyway, so that's the idea, yeah. Okay, so we can use, for example, this action model to capture this action. So maybe this is others, and I is Hans. So Hans know whether I wrote 0 or 1, and the others have no ideas. And maybe in a more complicated setting, so I is Hans, J is people in the room, maybe K is probably Jiang, who is not in the room and he is not sure. He thought nothing happened. Okay, and to use this kind of action models, we can handle some say full observational power, like Hans received the message and he knows whether this is a 0 or 1, or partial observability. You all observe Hans received something, but you don't know exactly what it is. And the non-observables, like Jam is outside the room and he doesn't know what happens. He believes nothing happens. So you can do this, and you do this epistemic planning using these things. Yeah. So. But some results about the limitations. So there are decidability results based on S5, S4-5, no common knowledge, no factual change setting. The bad news is unbounded plan using a plan existent problem for DEL is undecidable. Even you just have 2 agents. Yeah, so 2 agents is extremely hard than the single agent, because to have decidable fragment, either you restrict to the agent, you do the single agent thing, or you restrict the action model, you restrict the precondition of action models, and this and that, you may have decidable fragments. Yeah, but the single agent is relatively easy, yeah. Oh, sorry. I should have used another, yeah, the beep tech thing. Sorry, this is Bollander and Anderson. This is O'Shea and Bollander. This is O'Shea and Bollander. This is the Chinese team I mentioned in Guangzhou. Yeah. Yes, sorry, I forgot to change it. Okay, so some bad news. And other related epistemic approaches, I think this is Rajiv and Jam's approach. And also there are approaches where you can specify these plans by using some language, like program language. You see the Jeremy Long and others, but they only talk about single agent. Again, it's decidable. The complexity of plan existence problem is known. It's the same as the AI thing. This thing is, this is Bollander and his students, a new work where they talk about conditional DEL planning. Because in the traditional DEL planning, you just have a sequence of actions, but now they want to also have conditional. Under this case, you apply this action model. Under this case, you apply that action model, and they also discuss the complexity, decidability, sorry. But it's, again, single agent, because you only have hope for single agent. And the DEL like sequence calculus to handle this kind of planning job, but it's decidable, but the thing is, it's just one-step thing. You don't have plan for many things. It's just one step. And earlier work, you have model checking with alternating time temporal logic on finite models. So this is kind of a game logic where you can say, I know that with Hans, I can make sure Kamal will be happy in the afternoon, something like that. Yeah, so the thing is, the trouble is you have to have a finite, this temporal epistemic alternation model. I mean, but usually these models should be computed from some basic things, and you shouldn't have a finite thing. Although this is doable on finite model, I think it's model checking is in P, but it doesn't mean much, right? Because this model is too explicit. Yeah. Okay, so multi-agent situation calculus with action model, plausibility models actually, it's also done by the Chinese team, Yu Mei Liu and her student, and also recent PhD thesis of Thomas Bollender. I recommend you, if you like to study this kind of thing, to check Thomas Bollender's papers and his links, and you will see a lot. And of course, Hans did a lot of things on card protocols, but in our point of view, they should be called card plans. To, let's say, using card to let someone know, but not others know something, right? Yeah, this you can do, yeah. I also did some work in that. Yeah. Okay, but the questions that I want to get back to the critical part. So the thing is with, for example, with the dynamic epistemic logic planning, it's not so clear to me who is the planner. I mean, do you want to make sure in the end the planner will know that the plan will work or not? Because usually you just say, oh, there are, you can find the sequence of action models. In the end, someone knows something. But as I showed in this example, these 3 different plans, even you can make sure someone in the end knows something, maybe he doesn't know at the beginning. So this is something you need to think. And also, the more important problem is executability of action models. See, each action model is a kind of a global picture of not only actions, but also observability of actions. For example, if this example, I gave this, I give this piece of paper to Hans. How can I be sure that everyone is observing that, and everyone is observing everyone's observing that? This is just a simple action, but I impose so much reading out of it by using action models. So this is, I think, the biggest problem for DEL to handle. So there are recent works try to separate actions and observations, like also in Hans's work about this announcement with attention. So if you want to announce something, you need to get attention from others. Otherwise, it's not a public announcement logic. Public announcement, right? If I just announce something and you didn't pay attention to me, I won't have the same effect, right? This announcement cannot have the effect. So there are some works to separate these things. And also, more importantly, for multi-agent thing, you need to do local actions, not global action in the DEL sense, right? And you need to specify the actions using some language. There are also some works recently, yeah, but I didn't have time to put it here. And you need to, as Rajiv said, you need to have a nice domain language to describe the setting of the planning thing. And more importantly, for multi-agent planning, it's important to have communications, right? You cannot assume they share everything immediately. There must be communication. Then there are also concurrency in communication. Also in these joint actions, there is also concurrency. So it's a lot of work. And also, what about in the game setting? You have a different kind of goals and preferences, conflicting goals. How can we make sure that China and India will go together to handle something, right? Also, another real question is: do we find the real applications of higher order epistemic planning? I mean, we can come up with all these nice, simple examples, but are they really useful? Do we have a real problem? Are we just creating a nail for a hammer in hand? That's probably the most critical question. So, yeah. Okay, so much for these things. If I may. Oh yeah. Actually, this is more. This is not just critical, but this is. If you look at it from the constructive side, then there are a lot of things to do, right? I mean, yeah. Okay. So finally, I want to get back to the 3 logicians that Rajiv mentioned. This computer science, mathematician, and the thing. And actually, after so many days of DEL, you should understand this puzzle. So does anyone want beer? Then I don't know. Finally, someone says yes. Yeah, okay, but my point is not this. I want to really talk about actually Hans asked what are the differences between computer science and mathematician or philosopher. I want to discuss that. So I want to quote a friend of mine who is now in MIT about the self-image of logicians and the reality. So he said, logicians want to be mathematicians of mathematicians. So really tough, strong, beyond all this simple mathematics. Yeah, computer science of computer scientists, philosopher of philosophers. But yeah.
So your friend is a logician?
Yeah, he's a computer scientist. Yeah, he studied also philosophy in our university. So yeah, I think he also did the mathematical work. So I think he.
Then there comes a but, right?
Yes, of course. But the reality is, logicians often end up with being mathematicians to philosophers. That's the usual thing I feel in my department. And computer scientists to mathematicians. Yeah, all this. I mean, also philosophers to computer science, like Jam. Many people must think, oh, Jam is a philosopher. Yeah. But this is not bad, right? This is not bad. I mean, we're logicians. We are just some special people, right? And if you if you apply this thing, you will say, you will get back to this. I mean, if you know what I mean. Okay, the thing is, for me, mathematics is the most important thing is rigorous. Maybe also it shows some very hard things. And for computer science, you want it to be implementable. For philosophy, you want it to the point. Even you say something really wrong, but if it's to the point, if it can raise some questions, it's good. Yeah. So logicians should bring all these guys together and help to do some nice work. So sort of my suggestion to the audience, the student audience, if you are into the practicing so-called if you are practicing computer scientist, I think logic. You can take logic as just a guide to let you to think philosophically, have some sounds right ideas, which can give you mathematical rigorous proofs of what you can do and what you cannot do. But later on, you can just forget about it. Forget about the technical stuff. Just have this kind of feeling in your mind, and you try to find the most efficient way to work in practice. So maybe that's the use of logic for many people who are not really into logic. I hope it's just to give you some ideas, and you will think more deeply. But in the end, you can just forget about it and you do your own thing. But after this process, I think you will. Yeah. Thank you very much.